the Greek letter psi was going to be used to identify what did we call this thing, and the last half of the word is function. The hyphenated second part is function. It's probability function or wave function, either way. That had no physical significance. How did I know it has no physical significance?
It can be less than zeros.
These things can go negative, and probabilities cannot be negative. Probabilities really have to range between 0 and 1, where 0 is certainty of absence and 1 is certainty of presence. So the fact that this can go negative means there's no real measurable quantity inside. So it has no physical significance. However, the same argument is not so if I write this. Now that can have physical significance. Why? Because it never goes negative. So this will be okay as far as experiments and physical significance is concerned. And that must be related to the probability of finding the particle. It truly will be, for us, in the most general case, a function of x, y, z, and t. And when we're evaluating the absolute value of psi squared, we have to insert a specific x, y, z to represent a certain point in space and a specific time t to actually get a numerical value and evaluate this thing. So what I like to say, just as summary, even though it's really very incomplete, was to say that this is related to the probability of finding the particle there, then. I just use those two words because it's easier to remember. There, then means don't forget you've got to fill in a specific point in space and a specific moment in time. All right, where are we? Another thing we discovered was, interestingly enough, W is greater than C. Remember, W represented the speed of the de Broglie wave, and we discovered that the speed of the de Broglie wave is always going to be greater than C because the de Broglie wave represents a particle, and the particle's speed will always be less than the speed of light. Therefore, the wave must travel faster than the speed of light. And that's not inconsistent with anything because we've already said that the de Broglie wave has no physical significance. Therefore, the speed limit, Einstein's speed limit, does not apply. Okay, next thing we did was to look at a particle in a box. And the key issues to the particle in the box are, first, it was one-dimensional. So we're putting it in a one-dimensional box, basically limiting it to the x-axis. And it is, the structure of the box is infinitely hard walls, which means when the particle hits the wall, it is totally reflected with complete conservation of energy. And of course, it does not penetrate the wall at all. Now you might say at the very beginning that this is such a totally idealized situation, would have no real counterpart, and you're absolutely correct. However, this problem was chosen as an easy way to illustrate several of the fundamental facts in quantum mechanics. Excuse me. And they start out with, well, let's figure out what the wavelength is going to be. So here's our box, like that. There's the walls, whose potential, and notice that I use the capital letter V, almost like voltage. The walls of the box have the potential going to infinity, like this. That represents the infinitely hard walls. It's a one-dimensional box in the x-axis like that. And of course, the dimension of the thing was capital L, like that. And I'd like to figure out what wavelengths will fit. Well, the most important criterion, of course, is the boundary conditions. And that is the particle cannot exist at the walls. It is between the walls, not at the walls. Why? The walls are infinitely hard. Hence, therefore, once we realize that the particle the probability function must be 0 at the walls, then I can simply write down, well, we drew the pictures and we said, well, here's one possibility, of course. Here's the next possibility. Like that. And so on. This is a picture that you're eminently familiar with from our early days in studying wave phenomenon. So the wavelengths, lambda sub n, is going to be 2L over n, where n can equal 1, 2, theoretically it can equal anything like that. So there's an infinite number of discrete answers. And immediately you see the first important point in quantum mechanics is that things get quantized. You only have certain quantities allowed for answers. Well, P, the momentum of the particle, is written as h over lambda. P sub n is going to be lambda sub n if you want to stick it in like that. Kinetic energy is equal to mv squared over 2m, or if you wish, p squared over 2m. So I say right here, I've just made an assumption. What assumption have I made? Non-relativistic.
Yeah.
Okay. So I might note B significantly less than C. So we're doing this we're doing a classical calculation now. So we're talking about particles that are non-relativistic. So now the kinetic energy is going to equal, well, p squared, here's p squared right here. So p squared is h over 2L divided by n. This whole thing is squared, divided by 2m. And of course you see that we have, on top we have an n squared, h squared. Downstairs we've got 4 times 2 is 8, m l squared. So we have quantum numbers for the kinetic energy. Then we did the problem, and I think it's on the paper. You discovered that electron, 0.1 nanometer box. You should have known the solution. Excuse me. 38 n squared electron volts. Those are the allowed values for an electron, whereas the energy for the marble in a, what was it, a 10 centimeter wide box, ended up as 5.5 times 10 to the minus 64 joules, time, n joules, excuse me, n squared joules, like that, is the solution you should get there. And getting the solution is not hard at all. It's a piece of cake. The last thing I hope you notice is that, hey, when you're dealing with electrons confined to things that are about the size of an atom, then the energy spacing is significant. In other words, this kind of an experiment should yield quantum results. I should be able to do an experiment like this and verify that quantum mechanics, which claims quantized energy levels, is correct. However, if I did an experiment like this, the quantum levels are so incredibly close together, I can never distinguish one from the other. So, in a classical experiment, quantum mechanics suggests that you'll have extremely close quantum levels. And no way can you do an experiment and distinguish one from the next. Whereas in particle physics, where you're talking about small objects inside of atoms and that sort of thing, you should be able to do experiments that would test the ideas of quantum mechanics. So that's the point. The point is not getting the answer. The point is understanding what these answers mean. And so let me see. no, I'm gonna save that for just a second. Okay, so pretty much this is just review of things that we did on Monday. Now I would like to extend the work and simply quote for you the Heisenberg uncertainty principle. And I'm going to try to motivate it, but I'm not going to completely justify it. That is, imagine we want to find an electron. How do you find an electron? Well, you see it. You see where it is. The only way you can see an electron is to shine light on it. Let the light scatter off of the electron. Electrons are very small, so to get light to interact with an electron, you have to have a very small wavelength, don't you? So here's the electron that we're interested in. And what we're going to do is we're going to shine on it light, and here comes the photon. A wavelength short enough that it will interact. Do you recall, if you have the wavelength is long compared to the thing you're interacting with, just right on by. Doesn't even look at it, doesn't even see it. So you have to have a wavelength comparable in size to that which you're looking at. So of course this is a short wavelength photon. What does that mean about its energy? High energy photon. Strikes the electron, and of course the electron scatters in one direction, and a photon scatters in another direction, like this, and that act of shining the light on the electron disrupts the electron. So doing the experiment has an effect on the results. The electron would have behaved differently had you not looked for it. So that's what led Heisenberg to the idea that there is no certain information. Let me just quote results now. Heisenberg says that if you go looking for an electron, then the precision with which you know the position of the electron is related to the wavelength of the photon. The scattered energy or momentum of the photon is related to the wavelength. The shorter the wavelength, the more precisely you know the position of the electron initially, but the less precisely you know the scattering effect on the electron. So his result was, there's a certain uncertainty in the momentum of a photon, of an electron, a certain uncertainty in the position, and that is always greater than or equal to h over 4 pi. He was able to show that that is the absolute limit that you'll ever get for knowing the position and the momentum of a particle. So the more precisely you try to measure one, the less well you know the other. And this is the absolute limit to your ability. And it's important for me to say, we're not talking about experimental error. We're talking about this knowledge, this information doesn't even exist. No matter how cleverly you design your apparatus, you'll never measure more closely than this, because it's not an experimental failure. It's a lack of information. Similar analysis shows us that there is a certain uncertainty in energy and time greater than or equal to the same thing. But by the way, as many of you have already noticed in the book, h over 2 pi is often called h bar, just to cut down on the writing. So I'm going to write this as h bar over 2. That's the uncertainty principle. And for us, we're only going to deal with these two sets of variables, that is, momentum and position are related, or energy and time are related. That's the uncertainty principle. I'm going to quote it. I'm not going to derive it. But this represents the highest level of precision that exists when making these measurements. Now, to add to this, so that we can go on with today's lecture, we're beginning to notice now, especially this, there's a vast difference between classical mechanics and quantum mechanics. And that is, in classical mechanics, I could call it very deterministic. According to Newton, and I think everybody that existed between 1700 and 1900, it was believed that the more precisely you measure something, the more accurately you will know it. and that everything has a very specific answer. Along comes the 20th century, we begin to realize that no, there are no specific answers, there's only probabilities. That when you calculate an answer to a question in 20th century physics, you are calculating the probable answer, not the exact answer. And it seems quite out of keeping until you go back and think about this. When you're looking for quantum effects in macroscopic experiments, you're probably not going to find them. It's only when you get into very small systems are you going to be able to determine the difference between a quantum suggestion and a classical suggestion. So what I would call classical physics, let me just draw a little circle like this to represent, I'm going to call it CP for classical physics or Newtonian physics, was a world which seemed to work beautifully whenever we were applying Newton's laws to things like the motions of planets and that sort of thing. Along comes quantum mechanics, and it's actually a bigger law. Now, how I draw this thing. Now, quantum mechanics is a bigger law than classical physics, quantum physics. But it totally and completely encompasses classical physics. In other words, quantum mechanics does apply, let's say, to the orbit of the Earth around the Sun. It does apply. It would be a god-awful way to try to calculate what the orbit is, but it should work. And the most important thing is that whenever you apply quantum physics to a classical problem, which has already been measured, the quantum solution had better reduce to the classical solution. So, quantum physics takes into account everything classical physics does and a lot more. But it's only out here that you can actually see the quantum effects. And of course, I'm thinking in the early days of atomic physics, the physics of the atom. And then later, of course, it becomes nuclear physics, the physics of the atomic nucleus. So as a kind of a philosophical statement, first we show that quantum results in the classical world are meaningless. We talk about the uncertainty principle, and we talk about this incredibly precise level beyond which you cannot go. And that leads us to the idea that quantum physics is a bigger theory than classical physics was, but that it's extremely important that whenever you apply quantum physics to a classical problem, the solution reduces to a classical solution. That's going to be a correspondence principle that we use all the time. Before I erase this, let me check and see what's next. Yeah.
We have a test, if you will, the cutoff line between the relativistic physics and the classical physics we would have, and the quantum physics what would it be the difference between the orbital and the electron as far as the mass?
We have a very nice cutoff between relativistic and non-relativistic physics, and that is the rest mass energy of a particle. You're absolutely right. There will be no specific cutoff like that for the difference between classical and quantum physics. However, if you are at all dubious, do something like this. Calculate the energy levels in the new situation. And at least in this class, you'll always come up with an answer either like this, where the energy levels are clearly separated, or you'll get an answer like this, where they're clearly not separated. Because you can imagine that the uncertainty in any one of these levels overlaps the next level. So we're not going to have a specific cutoff. I know it's really comfortable to have that one for relativistic physics. We're not going to have it for quantum physics, but I'm never going to give you a problem that's right close to the order. It's going to be way classical, or it's going to be way quantum. Those are the kinetic energies. And typically we'll be dealing with particles that have either kinetic or potential.
So are you saying that, are you calling an electron just a particle, or, because isn't it the rest mass of the electron, isn't that the cutoff?
The rest mass of the electron is the cutoff. The rest mass energy of the electron is the cutoff for an electron.
Or an electron?
Yeah.
So what's the rest mass for a particle? If it's it's not.
You have to know the mass of the particle and calculate the rest mass energy. Did any of you do that? Did any of you get the rest mass energy of a proton? E equals m naught c squared, which is what? 1.67 times 10 to the minus 27, am I correct there? Kgs for a proton, times 9 times 10 to the 16 meters per second squared times the conversion factor. And the conversion factor was 1 electron volt is 1.6 times 10 to the minus 19 joules. And I can see that the joules here would go with the joules there, so I'll be in electron volts. Did I remember, would someone check me please, because I just pulled this out of my head, is the rest mass of a proton 1.67 times 10 to the minus 27? Okay, so would you do that? Do you come out with about 940 MeV?
Yeah.
Okay, so whatever particle you have, you just calculate its rest mass energy. So now we have, for a proton and a neutron, why don't we just call both of them approximately 1,000 MeV? That's the rest mass energies of a proton and a neutron. A neutron is slightly more massive, but not that much more massive. So you get a half an MeV is an electron, 1,000 MeV is a proton or a neutron. And whatever particle you're dealing with, you just calculate its rest mass energy. That's the threshold. That's the cutoff. Is that right? Did I answer what you were asking? I get off on my own tangent sometimes. I don't really answer the question. Did I answer the question?
Well, unless you specifically say meson particle, but if you say you just use the word particle, what do we assume it is?
No assumptions. If it's just a particle, if it's just a particle, and I don't say the mass of the particle, you're up the creek. You're up the creek with a lot of cattle, and that's what you say. Right? Up the creek with a lot of cattle, and I've got that name. That creek has a special name.
Shit Creek.
Creek with a lot of cattle at the other end. That's why it has its name. See, now you got it? Okay.
Without the cattle, though, you got nowhere to go. That's
Yeah. This is all thanks to my brother. He's full of nonsensical fakes, like running around like a chicken with a wing stop.
Sounds like that's what we ate.
All right, where are we? Oh, there's an interesting analogy here, and it's just a subtle analogy. It's not complete, but isn't it interesting that you remember in classical optics, if the wavelength of the light that you're using is comparable in size to the object off of which it scatters, then you look at light as a wave.
Okay.
And if the wavelength is long compared to the object that is scattering off of, light behaves as a ray. Remember that? Light is sometimes a ray, sometimes it's a wave. When is it a wave? Whenever the light goes by, what it's interacting with is comparable in size to the wavelength. I think about this. A buoy out in the ocean. A buoy is maybe a meter across, it's floating on the surface. If a little short wavelength goes by, let's imagine a boat goes by and it produces a wake. It's got a little short wavelength, that wake hits the buoy, the wake scatters as a wave, doesn't it? Whereas, here's the buoy sitting out there, and you get these long, 40-foot long ocean rolling waves. They come by, and the buoy doesn't scatter the wave at all. The buoy goes up and down like that. The wave goes by and doesn't even interact with the buoy. Long wavelength, little object, it doesn't interact. Short wavelength, little object, it interacts as a wave. Well, the same thing happens here. If the de Broglie wavelength is small compared to the object you're scattering off of, then it behaves like a billiard ball. And if it's large, it behaves like a water wave. So there's an interesting analogy between classical waves, whether they're a photon or a classical wave, and de Broglie waves, whether they're looked at as waves or particles. That's kind of interesting. Now, to get ready and use that piece of information, I want to go back to, and somebody asked the question, why do it like this?
So it has physical significance.
And I'd like to answer that. Because psi, in general, could be written as A plus IB. Oh yes, what is I?
Measuring number.
The imaginary number, or the square root of what? Negative 1, yes.
Take the opposite value of the
Hang on. So in the past, we've been dealing with things that were strictly measurable. And if you want to think about waves, we were talking about waves that were strictly measurable. So it only had a real part. But now we're dealing with something that is not measurable, therefore it may retain its imaginary part. So psi could be a complex number. Definition, and I'm sure you've seen this before, this is not new or exciting to you, psi star is going to be called the conjugate of psi. And all you do to conjugate anything, as you recall, is wherever you saw an I before, you put in a negative I. And you've got a conjugate. So by definition then, psi squared is psi star psi. And what happens is A minus IB, A plus IB, and of course we get A squared, and then you get a plus IAB and a negative IAB, so the cross term is gone, and you get a minus I squared B squared, but I squared is negative 1, isn't it? So we get A squared plus B squared. So that when you conjugate a complex number, and then you multiply the conjugate times the number itself, you will definitely always get a real and positive answer. So things are a little bit different now that we're allowing these things to get complex, and we have to do the conjugated part. Now, let's think a little bit more about something I said earlier, and not earlier today, and try to interpret it. What does this mean? Well, let's start with this. Let's start with psi squared dV. That's the probability of a particle within this differential volume. Now, what I really wanted to ask was, when I integrate this thing from minus infinity to infinity, what am I doing? I'm adding up all possible probabilities, right? So I search. The way I like to think about it is, if I'm integrating from minus infinity to infinity over volume, if I'm integrating over volume from one infinity to the other, of course, I'm searching all logical space. And what I'm doing is I'm adding up all the probabilities from all the places in space. So clearly, if this thing turns out to be if equals 0, there is no particle. You search all of space, and you have a 0 probability of finding the particle. There is no particle. If it ends up equaling infinity, then the particle is everywhere at all times. So both of those answers cannot represent a real particle, can they? These two cannot, they cannot represent a real particle. So if you do this integral and you come up with either one of those answers, then this psi wave does not represent a real particle.
Since psi is a probability wave, but it's psi squared right now, is that going to change how it comes out? So like we have to square root the answer?
It does, because if you were talking about just side, then you would end up with an imaginary part which is not measurable.
So if God were a particle, he would have infinite probability.
I wouldn't touch that with a 10-foot pitchfork.
Good man.
Well, you think about it, you just physically explained the philosophical.
Have you met my neighbor?
Yes.
She's a Baptist preacher.
When you said that a psi-squared absolute value is equal to probability,
Yes.
now you're saying that psi-squared.
I'm not quite there yet. I'm not ready yet to say it is the probability, but I'm getting close. The first thing I'm saying is it's related to, and clearly, however it's related, if you give either one of these answers, you've got something that's insane. You've got God or the devil. But I'm heading right towards what you're asking. I'm heading right for it. So stand by, just stand by a moment.
I would assume the devil's nowhere.
The devil is nowhere.
It's not difficult.
The devil does not exist. So what if you get 666? Also, this answer cannot be negative, nor can it be complex. That doesn't make any sense either. It shouldn't turn out that way based on what we said before, but all the answers that are not acceptable are, if you do this integral and it turns out to be 0, infinity, negative, or complex, you do not have a real particle.
So complex would be like the Easter Bunny.
The Easter Bunny. I know I should have let this get started.
You should have just started.
That's what my wife said. You come up to a 4-way intersection, 4 stop signs. 4 cars come up absolutely simultaneously. They all come to a stop simultaneously. One car is the perfect man, the other car is the perfect woman. This car is the Easter Bunny, and over here is Superman. Who gets to go first?
Superman.
In her opinion, the perfect woman, because the other 3 are just figments of your imagination. I usually tell the joke different. How did we get out of this?
That's the middle.
Now, if we have this, look, the integral of psi squared dB equals 1, here we go. If it equals 1, then we call this wave function, the wave function is normalized. And that's a task that's going to be left up to you from time to time. You're going to need to normalize the wave function. Not by integrating to c that equals 1, but you're actually going to adjust the constant out front to force it to equal 1. So one of the very first tasks you normally have is to normalize a wave function. You take a wave function, you integrate it and say that the integral must equal 1. And you do that by adjusting the constant out front. That done, now you have a normalized wave function. And now we have exactly what you were asking a moment ago. Now we have a wave function which is directly equal to the probability of finding the particle at a certain point at a certain time.
Are the limits always going to be negative to the infinity?
You know what, I'm glad you asked that, because what I like to think, instead of negative infinity, they always go like that in the textbook. But I like to think in my mind, I like to think that the integral is over all logical space. And if you're wondering about that, think about the particle in the box. We know for sure the particle is between the walls. Who needs to integrate from negative infinity to positive infinity? Who needs to do that? It's between these 2 limits. So in all the definitions I always see, it does range from negative infinity to positive infinity, but in reality, think to yourself over all logical space. If you could eliminate part of space, there's no sense in integrating over that.
We don't have to have a time factor in it too, since it's depending on the time as well.
One does have to have a time factor in there if one is not in a steady state. Fortunately for you and I'm going to see to it that all of our problems are in steady states and nothing changes in time. But that's not possible.
What is the implication of the coefficient to?
Say again?
What's the implication of the coefficient to normalize the probability?
Let me do it for you. I'm going to do it in just you're about 2 steps ahead of us constantly. You're good. You're good. You know which direction we're going, huh? By the way, I want to tell you a couple more things about psi. Very important. First off, of course, it must be single valued, huh? Because how could you have 2 probabilities at the same point in space at the same time? So it's got to be a single valued function. It also has to be continuous. That is, if it has a certain probability of being this point, immediately adjacent to it, it has to have a similar probability. It can't have a quantum jump in probability. So the thing has to be single valued and continuous. And then we're going to discover through momentum considerations that the wave function and its derivatives must all be finite, continuous, and single valued. They must have a finite answer, be continuous, and single value. So another test you're going to apply from time to time, when I give you a wave function and say, could this wave function describe this particle? The first thing you do is you test the wave function and its derivatives to see that it is finite, single valued, and continuous.
Would it be considered a wave function if it wasn't continuous, right? The wave has to be continuous?
Say it again?
It wouldn't be considered a wave function if it wasn't continuous.
Actually, we can find wave functions which are discontinuous and mathematically acceptable, but physically not, because they are discontinuous. And that's the judgment criterion. It's not just going to be mathematically acceptable, it has to also be physically acceptable. So what I'm giving you now is physical acceptability. So, what did I say? Psi must be single valued, continuous, and finite, so must its derivatives for it to be a physically significant wave function. All right. And finally, now, here's the part where we're really going to get around to starting to calculate what's going on. Of course, if I write it like this, here's the integral. Psi squared dv, let's not say dv, let's say dx, okay? Psi squared dx from x1 to x2, that's the probability. We will find a particle between x1 and x2. And as you can see, we're getting around now to where we can actually do an experiment. If we have a wave function and we integrate over this one little area of space, it tells me the probability of finding the particle in that area of space. Now we can do an experiment and find out if that probability prediction is correct. So instead of just making sure that it's normalized, the next thing you do is then start to inspect little areas of space to see what the probability is in just small areas of space. To do that, I want to review with you very briefly something that we talked about recently, and that is, what is this creature right here? D squared y dx squared equals 1 over v squared d squared y d squared. That's a classical wave equation, isn't it?
Yes.
And y was the wave function that we dealt with. You remember we had things like this, I think. We had that y was some kind of a function, and that is of t plus or minus x over v. And we put in a function like that, and I think we used cosine, didn't we? And we played around with that a little bit. Well, for us, we're going to consider a wave function for a free particle. And a wave function for a free particle means a particle which is moving with a constant speed. It's not under the influence of any force, so it's moving along at a constant speed, and pursues a straight line, of course. And our wave function is going to be tantamount to a standing wave. And you can think of it like this. Imagine the particle in the box. And the particle in the box is bouncing back and forth. Of course, it's moving at constant speed. It's moving back and forth like this. That means the probability at any point in the box is always the same. It never changes. Once you get into equilibrium, now here's that dynamic case you were kind of asking about a moment ago. I'm not going to allow the particle to be dynamic. I'm going to allow the particle to be in steady state. That is, it's moving back and forth at constant speed, straight line like this. Every time it hits the wall, it just instantly reverses its course like that. So the wave function, which represents the probability of the particle in the box, the probability doesn't change. Whatever the probability of finding the particle in the center is, it's always going to be that. Whatever the probability is finding it near one end or the other, it's always going to be that. So what we're going to have is essentially a standing wave. So our wave functions are going to be tantamount to standing waves when we were dealing with the original wave function. Oh, what was that, a month or so ago? The appropriate choice here, and you're going to look at this and say, but why? Yeah, that is y equals a e to the minus I omega times t minus the same thing, x over v. And I'm suspicious when I see a negative sign there, what do I suppose this is referring to? Particle moving in a positive direction. Now, but you're looking at that and you're saying, well, wait a minute, that doesn't look at all like we were doing before, does it? Doesn't look at all like that. But please recall that e to the minus I theta is cosine theta minus I sine theta. You probably remember that from trigonometry. And of course, when we were talking about real strings, like a string on a guitar or something like that, we would just ignore the imaginary part because we're talking about a real string. There's no imaginary part that we're going to measure. So you can see that we had a function that we dealt with, the cosine function. Now, unfortunately, we've got to include this. Well, it's not such a big deal, but at first you say, oh my goodness, now we got an imaginary part. That imaginary part might turn real. Remember? There's the coefficient on the imaginary part. We might have an actual, real, measurable coefficient from the imaginary world. You and me and Alice, right? Alice in Wonderland. You should be playing that Jefferson Airplane music like All right, so now what we're saying is that the appropriate function that would fit in here would look like this. Y would equal A cosine of just the argument, which is omega times t minus x over v minus I A sine of the same thing, omega t minus x over v. And like I say, in the classical world, we just ignored that because it didn't mean anything in classical physics. But to us now, it might mean something. That v does exist over there. So let's see where this leads. If this wave function is essentially the same wave function we dealt with in the past, let's use this same wave function now in the quantum world and include this term to check and see if the b is real, if the b actually does come up. Let's check it out and see. So now I'm suggesting that a logical wave function, which would represent a standing wave and eventually the particle in the box, is going to be that psi equals a e to the minus I omega and then t minus x over v, like this. Lovely. We've got a good start. We have a start here. What have we started? I don't know. Let's see. But remember, recall that omega, do you have to remember the name? Omega is not No, I'm not gonna say anything, see if anybody remembers or recall or make. Is that what you were gonna say? Angular frequency? That is correct. 2 pi nu. 2 pi, there's the angle, right, in radian measure, times nu, which is what? Standard frequency. Also, v, the velocity of the wave, is simply the frequency times the wavelength. Frequency times the wavelength. So we can replace both creatures now, and we can say that psi equals ae to the minus I times 2 pi nu t minus x over v, which is nu lambda. If we put the nu in there, then we get ae minus I times 2 pi. I'll get rid of that in just a minute. And we have nu t minus x over lambda. And now this makes us a lot happier. Oh, am I happy? Yes, you're happy. And part of the reason it makes you happier is because clearly now the units work out. I don't know if you were looking at it at this point and wondering about the units. You should have been. But I say here, clearly the units work out. Can you tell me why? This has no units, huh? This is seconds times hertz. This has no units because this is meters divided by meters. And of course, the argument up here better have no units in it. So when you looked at it like this, I wonder if you thought to yourself, geez, I wonder if there's units that I have to worry about. You get down here and you say, no, no worries. I'm as happy as an Australian. Aren't they the ones that say no worries? I'm as happy as an
I guess so.
Australian.
I think that's,
General Australians are happy.
that's Africa.
We're almost as happy as, who else is happier than Australians? The Trumpers. But I'm going to fix it up right now because E equals H nu and P equals H over lambda. So notice then, in place of nu, I can write E over H. And in place of lambda, I can write H over P in this original equation over here. So let's do that. Oh, I did one other thing. I guess I can do that here. Notice I could write this then as, where did I do? Oh, here. I wrote it as E over 2 pi h bar, and lambda is written as 2 pi h bar over p. Why did I do that? Let's go, oh, well, obviously I'm trying to get rid of this 2 pi here, that's all. I'm just trying to get rid of that 2 pi right there. Which we have done. Let's fill this thing in. I'm going to copy off of my notes, and then I'm going to check and make sure that everything looks good from one board to the other. I can't see that board from here. So I claim then what we have is that psi is equal to A e to the minus 2 pi I times T e over 2 pi h bar minus x p over 2 pi h bar. Now let's see if I substitute it in properly here. So for E and some of the new, okay, those good. And then what was the other one we're substituting for? Oh, we're substituting for lambda, but 2 pi p was on top. Yeah, looks good. And you see, I have gotten rid of the 2 pi. That's why we did that. We got rid of the 2 pi. And there's an h bar in common in both places. So finally we have A e to the minus I over h bar times et minus px. Aha! Look, we're starting to see Heisenberg in here, aren't we? Momentum times position, or energy times time. We're starting to see Heisenberg in here. Pretty clever. Even if I do say so myself, and I just did. All right. Well, I'm pretty excited. I really can see, there's a light at the end of the tunnel. You see that? It's the train.
Yeah.
Now, let me take just a moment and ask you to do the following thing. Would you please find these two things? Please find d psi dt and d psi dt and d squared psi dx squared. Would you please find those two? I'll write them on the board in just a moment, but I'd like you to find those two for me and then compare them.
The A is constant, is that correct?
Correct. A is constant. Once you differentiate this once with respect to time, you really only get this argument out minus IE over h bar, then you get the wave function back again. Or if you doubly differentiate with respect to space, then you're going to get negative, negative, and an I squared, so that's that negative sign. You're going to get the P squared over h bar squared, and then you're going to get the wave function back again. So the differentiation is really pretty easy. Why did we do that? Well, I think I know. Because in a classical use of this information, I can think in terms of E, total energy of a particle, is equal to P squared over twice M plus V. And I'm using a capital V there. It is not velocity. Do you remember what I was using the capital V for? Correct. Potential. Potential energy. So, this is really just classical physics, isn't it? Energy is equal to kinetic energy plus potential energy. And it will be useful to us if we multiply both sides of the equation by psi. So here we go. E psi equals P squared psi over twice M plus V psi. And notice we have got an expression for E psi and P squared psi. And it's really pretty easy to write down that E psi is going to be H bar, d psi dt. And then for the P squared, you see the P squared is right there, just move the negative sign and the H bar upstairs, so we get equals minus H bar squared over twice M d squared psi dx squared. And what about the potential? We don't know yet. V psi.
So are you using that as PE or potential difference? The V.
It is potential energy.
So it's PE.
Potential energy, yes. Not voltage, but potential energy. And you say, I am so happy now, I can't stand it because we are now done. We have our wave equation. Our equation, which is now tantamount to the earlier wave equation in classical physics. Does anybody know the name of this equation? This is Schrodinger's equation, ladies and gentlemen, Schrodinger's equation. S-C-H-R-O-D-I-N-G-E-R. You got to put the little dip up there, right? Because his name is German, and we have to pay him proper respect. So we pronounce his name properly. It's not Schrödinger. It's Schrödinger. You got to say it like a German. Schrödinger. Okay. You may be tested on that. Schrödinger. This is Schrodinger's equation, time-dependent form, one dimension. Schrodinger's equation, time-dependent, 1D. You'll say, well, that's lovely, but what about 3 dimensions, right? We live in a 3-dimensional world, not a 1-dimensional world. Does this equation apply? Sure, it's really easy to rewrite Schrodinger's in 3D. It looks like this. Well, time, I, H bar, d psi, dt, doesn't change. But what we have is minus H bar squared over twice M times d squared psi dx squared plus d squared psi dy squared plus, and of course the z term, unless you're English, then it's the z term, plus v psi. Now, many of you have already taken your differential equations class, and you see this, oh, this is a nice, cute little differential equation. And you know exactly what to do. You seek psi that satisfies the equation. And when I say that, you seek a psi, you seek a psi that once you place it here, here, and here, that equal sign actually holds. Right? Isn't that what you do in differential equations? You find a function that fits into the wave equation where once you fulfill this requirement and this requirement, you ask, is it equal? If it is equal, then mathematically you have satisfied Schrodinger's equation. Now, fortunately, you're going to get a great sigh of relief when I tell you, you are not going to be asked to find psi. I will give you candidates and ask you, are these legitimate wave functions? So what you do is, the first thing you do is you stick it into Schrodinger's equation, and you ask, let me put it in red, I don't have red, so I'll put it in orange. The first thing you do is you insert it here, and you ask this question, does that equal sign actually hold? If the answer is yes, then you have a candidate. It's not necessarily a legitimate wave function yet, but you have a candidate. You also have to put it to those other tests. That is, now you have to integrate it over all logical space. Is the answer finite? Not zero, not negative, not infinity, but is it finite? Is it single valued and continuous? Is its derivatives, and I mean particularly the XYZ derivatives, not the second order, but the XYZ derivatives, are they also single valued, finite, and continuous? You've got to answer all of those in the affirmative before your candidate becomes a real logical wave function. That done, you know what's next? Do an experiment and see if the predictions come out correct. So you got to do a lot of theory before you do the experiment. Where am I now? Still up front, huh?
So are you going to show us how to do what you said?
Yes. You don't think I'm going to leave you out in the woods like that, do you?
Sure I do.
Sure I do.
Yeah.
That's the way I am. That's the way I do things. By the way, before we do that, before we give our first example problem, I want to inform you that we did not derive Schrödinger's equation. What we did was simply arrive at Schrödinger's equation. Schrödinger's equation is a first principle. There is no more fundamental principle from which you derive Schrödinger's equation. Schrödinger's equation is a first principle. All we can do is postulate Schrödinger's equation is the important equation. M will notice that H nu prime, H nu plus M, H nu over C squared, G, H. Factoring out the H nu, we end up with 1 plus GH over C squared. Is that agree? 1 plus GH over C squared. Lovely. In 1960, two experimentalists, Pond and Ripka, working at Harvard, decided to do this experiment. And they wanted to test and see if photons do actually respond as general relativity says they must. And in their experiment, they simply, any wave which represents its amplitude at any given point represents the probability of finding the particle at that point. So things change a little bit. Where did they change? For a single particle, and its probability is spread out along the x-axis, Ni at xi, instead of talking about the number of pennies at a particular point like that, that gets replaced with the probability, P-R-O-B, I'll just write probability, P-R-O-B, that you're going to find the penny within dx at x. So, the probability at any given point is given by psi squared at that point times dx. Hence, therefore, I'm going to change things just a little bit because we're going to be dealing with differential elements, so the summation will be replaced by integrals. And instead of talking about the average position of a penny, what I'm going to be doing is talking about the expectation value of the position. And that is going to equal, well, we just replaced, that's all. I'm looking right here, and we're replacing right here. We have the integral from minus infinity to infinity of x psi squared dx divided by, and then it's just the number down here you can see, so it's going to be the integral minus infinity psi squared dx. Outstanding. We now have a way of making a prediction of the most anybody notice, I'm sure you've noticed this, haven't you? If normalized, then what? What did you recognize? Anybody see it?
Equals 1.
The denominator is 1, isn't it? If it's normalized, then the denominator is 1. So the expectation value, if normalized, is just the upper integral over all logical space for us right now, minus infinity to infinity, of x psi squared dx. So this is my first hint at how you get around to actually interrogating a wave function. Interrogating a wave function, asking, give me a result I can test. Allow me to do an experiment, and that's how you do it. By the way, what we did in general works for any observable. So typically in the textbooks, you're going to see something like this, g of x. The expectation of anything, not just position, is easily calculated as, you just put the g of x, whatever that is, here, and then multiply it times the absolute value of psi squared dx. So it's a generalized result now, but you do have to be careful. The expectation value of energy or momentum is not quite as simple. I'll be showing you how to do those two a little bit later. So here's our first attempt at being able to measure something once we've made a prediction, once we have found a wave function that works. And I'm going to simplify things even further. I know you're sitting there saying, this looks like a cakewalk. This is going to be simple.
Actually, no, we're sitting here still wondering how we use that equation.
I'm going to show you. But before I show you, I'm going to make it even easier than that equation appears right there. So what I'm going to do right now is just make life so simple, you're just going to not know what to do.
So what do we need to know the average x part? What is that for?
That is how you interrogate the wave function so that it will make a prediction that you can test with an experiment. The wave function is an ethereal thing. And make a prediction that I can do a real experiment and find out if you're right. So, put a particle in a box, and this will tell me the expectation value of the particle in the box. Now I can go look and see if it truly reflects what the experiment says.
So what does n equal? Just that one particle?
In this case, n, this total n is 1. Yes.
Okay.
It's all the little probabilities added up. They must add 1 if the wave function has been normalized.
If I have 10 particles in that box, is n 10?
You're doing a different experiment then.
Well, see, that's what I'm saying. Maybe you better actually use this so we can understand what you're saying.
We're going to, but we're not ready to use it yet. You're jumping ahead. That's what this table does. You're jumping ahead. But like I say, let's make it simpler so we can really have some fun with it. Starting with our original wave equation, psi, which equals AE to the minus I over H bar times ET minus PX. Of course, you'll notice now I can write that as AE to the minus IET over H bar times E to the IPX over H bar. Minus IET over H bar, yes. IPX over H bar, yes. How lovely. Let me please write this as, please excuse me, psi E to the minus IET over H bar. And you'll notice now what I'm calling lowercase psi is A e to the IPX over H bar, the spatial part. And then I left hanging out here in space, shouldn't use that word, I left hanging out here by itself the time-dependent part. So capital Psi is small case psi plus the time-dependent part. So what? What am I doing? Let's stick it into Schrodinger's then. Oh, Schrodinger's gone. So we'll put Schrodinger's back in there. We're going to put it here. I h bar d psi dt equals minus h bar squared over twice m d squared psi dx squared plus b psi. We're going to stick this right in there. And of course, when we differentiate once with respect to time, we're differentiating this creature, and we get just the argument of this out front and get it back again. So we get I h bar times minus I e over h bar psi e, to the minus I e over h bar t equals. So I'm going to put this here in parentheses, because all I'm doing is pointing out argument out front once I differentiate once with respect to time. And then you get the thing back again. And of course, this part is spatially dependent, so it does not get differentiated. Next, I get the minus h bar squared over twice m. And probably the easy thing to do right now is to just write this as d squared small case psi dx squared, yes, times e to the I e over h bar t, because I don't differentiate that. I differentiate with respect to space and not time at this location. And then finally, I have plus v psi e, the same old thing, I e over h bar t. Negative. Negative. Wasn't that fun?
Yeah.
Well, I got those negatives in there before you noticed it. You noticed it, huh? You just would be polite and saying it.
Something like that.
And of course, in common, we've got this term everywhere. This term is in common everywhere. So it can go away. And what do we have? I have no idea. We have I squared with a negative sign, so that's just 1. H bar E over T. H bar, oops, no, H bar is gone too, huh? We have H bar E over H bar psi, so it's just E psi equals minus H bar squared over twice M D squared psi dx squared plus V psi. And all of a sudden, the time dependence is gone. Let's rearrange, because we like to rearrange. Huh? Go ahead.
Why isn't there a negative I squared in front of the e?
Well, there is. A negative I squared is plus 1.
Oh, yeah.
And that's,
Yeah,
your section partial with respect to x is now the lowercase I.
correct.
Why is that?
Because I took the lowercase out so that I could differentiate it with respect to x, and leaving the time-dependent part so that I can cancel it away. See, if I put in there, if I put in minus h bar squared over 2m, if I put in capital psi, then capital psi is the spatially dependent part and the time dependent part.
Okay.
So I wrote it like this because I knew I wanted to get rid of this. What were we doing? Oh, we're rearranging. So let's just move everything that way. And what we get then is, let's see, d squared psi dx squared plus 2m over h bar squared times e minus b psi equals 0. Let's see if I did my algebra correctly now. D squared psi dx squared 2m over h bar squared e minus b psi equals 0. Yes, we now have the time-independent form of Schrödinger's equation, usable anytime you have a system in steady state. A system that is not changing in time, we can use the time-independent form of Schrödinger's. Of course, this is time-independent form of Schrödinger's in one dimension. And what would you expect I was about to write if this is 1D, Schrödinger 1D. What do you think I'm about to write if I want to write Schrödinger's equation in 3D? D by dx squared, d by dy squared, d by dz squared. Just add those up. That's all. All right. Golly, we've been having fun. And we're halfway through. I figured we'd be done today.
We're only halfway through.
To solve Schrödinger's equation is to find psi that obeys the equation and the boundary conditions, but is also well behaved. By the way, I should define that for you. Remember the earlier part where I said the wave function has to be finite, single valued, and continuous? Its derivatives must be finite, single valued, and continuous. All of that is subsumed in the statement well behaved. So when I say that the equation is, when I say that the wave function is well behaved, I'm implying those 6 tests. It passes all 6 tests. So instead of going through all 6 tests every time, I'm just going to use the term well behaved. So to solve Schrödinger's equation is to find a psi that obeys the equation, obeys the boundary conditions, and is well behaved. So the first thing you do is you put it into Schrödinger's equation and ask, does the equal sign hold? If it does, great. Then you ask about boundary conditions. Remember the particle in the box. The boundary conditions require that the answer be 0 at the walls. Okay, so it does. Next thing you do is check for well behaved. The wave function and its derivatives. You check all of those things. So that set of tests is what you do. You don't have to come up with a wave function. I'm going to give you a candidate wave function and say, could this wave function be correct? You go through all the tests and you say, aha, we have a valid wave function. The last test you will not be required to do, that is, make a prediction, do an experiment to see if it's right. Yes?
Can you repeat, you said it must be well behaved, obey boundary conditions, and what else?
What did I say? I said it must obey the equation, must obey the boundary conditions, and be well behaved. And then, like I say, the last test is one you don't have to do. That is where you make a prediction, do an experiment, see if it's right. And our next task is going to be just what Terry asked us to do, that is to solve a problem, and we'll save that for, geez, I'd like to do it on Friday, but you guys won't be here. We'll save that for Monday. That's okay, none of this is on that set of questions that I gave you. The only thing that really is new on that set of questions that I gave you this morning was the uncertainty principle. All right, folks, thanks for being here.